Alright, welcome back to the channel. In the last video, we talked about the AI needs tools, how to communicate between AI and tool, and why a standard like MCP is necessary. Today, we are diving deeper into the MCP fundamentals, what it's made of, how it works, and why it's such a game changer. First, I will let you know about core components about MCP. Let's start with the core building blocks of MCP. MCP is based on three key roles. First is host. Host is the environment. You can think of it as the platform that manages the conversation or AI application like Cloud Desktop or Cursor. Second, client. Client is a component within the host applications that manages communication with a specific MCP server. Third one is the server. This is where the tools live. For instance, calculators or search engines, databases. Now here's the cool part. The LLM doesn't need to know how to format for calling. The server doesn't care which LLM is calling it. And the host and client mediate between LLM and MCP server. This separation makes MCP scalable and reusable across different AIs and tools. Okay, so how does a model even know what tools are available? To describe available tools, the client sends a tools list request. Then the server responds about tools information. It includes tool name and description, which is what the tool does, and input schema, what input it needs and required, which argument must be set. For example, our get weather tool might look like this in MCP. This means the model knows exactly how to call the tool and what kind of answer to expect back. No guesswork, no messy parsing, just clear contracts. So let's say the client wants to call a specific tool. In that case, the client sends a tool's call. This way, the client and server can communicate with each other smoothly. Now, let's talk about how MCP actually works under the hood. Instead of custom APIs or imports, MCP uses JSON-RPC 2.0. The MCP client and server communicate through request response using JSON format and lightweight JSON-RPC 2.0 protocol. This design choice makes the MCP incredibly flexible. First one, tool calling works like a client-server system. In the previous video, we just talked about local Python function, but it doesn't need to be local Python function. Tool can be external API. The AI sends a structured request to the tool. Tool makes the result following by the LLM's request. LLM gets the tool's result and then continues generating its response. Second, we want to use existing tools easily. Like I mentioned right before, tool doesn't need to be local function. It can be any API which we can connect to through internet. In this way, MCP should support network communication, not just the standard input-output in local network. And third, we want a stream service. Many users want real-time results. Most LLMs generate text token by token, so we don't want to wait until the full response is ready. And fourth, tool developers don't want to make a complex API server for making the tools. Even though creating a web server is easier today than it used to be, it's still a bit of a hassle. Most developers just want to define their tool's input and output format, run it, and let it work with AI. They don't want to deal with a full-blown HTTP endpoint, routing, or server management. MCP solves this by letting tools speak a common protocol, JSON-RPC 2.0. With this, any tool can communicate with the AI without needing to become a web server. This makes it much easier for developers to create and share tools, while AI can still interact with them whether the tool runs locally or another machine or in the cloud. For supporting this, MCP selects JSON-RPC 2.0 protocol and supports multiple transports like STDIO. Is great for local tools. And second, streamable HTTP is perfect for network tools. Now you might be thinking, well, isn't this just function calling? Well, not exactly. Let me explain why MCP is actually a game changer. Function calling in models like GPT is great, but is tied to the platform. For example, OpenAI defines its own function format, Anthropic defines another one, and so on. MCP goes further because it's a protocol, not a feature. It standardizes tools, definitions, discovery, and communication in a way that works across all models and hosts. So instead of rewriting the same function definitions for each platform, MCP gives us a universal layer. But here's where it gets interesting. The adoption story has two sides. It really depends on whether you are an end user or a developer building apps. For end users and desktop tools, MCP is incredibly smooth. CloudDesk, just copy-paste a JSON config file and you're done. Click the Edit Config button to open the configuration. CloudCode, same thing. It's a really simple setup. But if you're a developer for building apps, then that's where it gets more complex. Many other AI providers support MCP now, but it has a slightly different format yet. For instance, OpenAI API MCP connector is like this, and the Anthropic's API MCP connector is like this. You can see the format is slightly different, but you don't have to worry too much. The good news is that popular developer tools are stepping in to bridge this gap. For example, LangChain now has MCP adapters that handle all the complex integration work for you. So instead of writing dozens of lines, you can just use their pre-built connectors and focus on building your actual app. So to recap, we have learned MCP is built on host, client, and server OS. MCP client send the tools list requests to know which tools exist and the spec of tools. Client sends the tool's call request to call the tool in the MCP server. MCP runs on JSON-RPC with STDIO or streamable HTTP for maximum flexibility, and it goes beyond the function calling by standardizing everything. In the next video, we'll look at MCP in action with a real code example. So see you later.